This video is going to go over everything you need to know about thermodynamics in AP Physics 2. The first concept covered in thermodynamics is the ideal gas law. This assumes that particles don't interact and particles don't take up any volume. The variables for this formula are volume, pressure, temperature, number of moles of molecules, and R, which is the ideal gas constant. All of these variables are connected by the formula P times V equals N times R times T. P corresponds to pressure, V corresponds to volume, N corresponds to the number of moles of molecules, R corresponds to the ideal gas constant, and T corresponds to temperature. In 1 mole, there are 6.02 times 10 to the 23rd molecules. There are two different forms of the ideal gas law. The molar form is the formula that we covered earlier, PV equals N times R times T. R will have two different values depending on which units you use, which is important to note because this will change the units you need to plug in for pressure, volume, and temperature. For the first value of R can equal 8.31 joules per Kelvin times moles, which is equivalent to newtons divided by meters squared times meters cubed over kelvins times moles. When entering values in for this, pressure will need to be in pascals, volume will need to be in meters cubed, and temperature will need to be in kelvins. The reason I broke joules up into newtons per meter squared times meters cubed is to show you what the variables correspond to. Pressure corresponds to newtons divided by meters squared, volume corresponds to meters cubed, and temperature corresponds to Kelvin. For the next value of R is equal to 0.082 liters times atmospheres divided by Kelvin times moles. Here, pressure corresponds to atmospheres, volume corresponds to liters, and temperature corresponds to kelvins. I did not need to break the units up any farther because each variable corresponds directly to the variable in the formula. The next form is the molecular form, with PV is equal to N times Kb times T. It is called the molecular form because it involves the number of molecules, rather than the molar form, which involves the number of moles. For this formula, all the variables are the same except for capital N, which is the number of molecules, and Kb, which is Boltzmann's constant. Boltzmann's constant corresponds to 1.38 times 10 to the negative 23rd joules per Kelvin. We can break this into newtons divided by meters squared times meters cubed divided by Kelvin. If you use this formula, pressure will need to be in pascals, volume will need to be in meters cubed, and temperature will need to be in Kelvin. As you can see, the variables correspond to the units in the Boltzmann's constant. The proportional form essentially combines the two forms that we were using earlier. It says that if the number of moles is constant, N times R and N times Kb are both constant. This then means that P times V divided by T is also constant. The most common scenario that this will happen is when there's a closed container and the number of molecules in that container is constant. Because it is constant, we can make a comparison from state 1 to state 2 with P1 times V1 divided by T1 is equal to P2 times V2 divided by T2. The only thing you need to remember for this is that the units need to be the same for both sides of state 1 and state 2. Another important concept is the kinetic molecular theory, which looks at atoms at a much smaller scale. We are essentially understanding the equation PV is equal to N times R times T at a micro scale. Using this mindset, we can understand pressure at a deeper level. Pressure here can basically be thought of as particles just bumping into the sides of the container. You can see these particles as they hit, they're causing a force, which combined together causes this total pressure. Temperature can also be looked at this deeper level. It's basically an average kinetic energy of all particles, where kinetic energy is equal to 1/2 mv squared. Basically, you can think of all the particles in the container having their own individual kinetic energy of 1/2 mv squared. Then, if you add up every individual molecule's kinetic energy in the container and divide it by the number of molecules that are in the container, you'll get a number that is proportional to the temperature. Finally, Maxwell-Boltzmann's distribution curve realizes that air molecules travel at different speeds. This means that a distribution curve can then be made of these different speeds. For the graph, the number of molecules is on the y-axis and the speed, velocity, is on the x-axis. A graph like this can help to show how speeds of molecules are distributed. Some helpful things to know is that directly below the peak is the most probable speed. Then, the average speed is to the right of this because the graph has a longer tail to the right. The root mean square speed is also another valuable quantity on this graph. It says that the root mean square velocity is equal to the square root of 1 over n times a quantity v1 squared plus v2 squared plus v3 squared, continuing on and on depending on how many velocities you have. This value is useful because we can find the average kinetic energy with the root mean square velocity. This is because the kinetic energy average is equal to 1/2 m times the root mean square velocity squared.